Well, it's time. Welcome back, folks. Sorry, the spring break is over. They always seem to go by really, really fast, but welcome back. We're in the final stretch of the semester, 6 weeks to go, including week number 11. And with where we're at so far, we're midway through the notes in 4.4, or just about at the midway mark. Then we'll be starting section 4.6 this week as well. And this one's going to bridge the gap between differentiation and the new topic of integration, which we're going to round out the course with. Other big announcement, well, not really a big announcement, but other announcement is I have a dentist appointment tomorrow. I'm not super excited about. It's on April Fool's, which doesn't seem to be the funnest thing in the world, which is going to overlap with our office hours. So I have a cancellation on that day, but we'll have class as normal on Thursday. But once again, welcome back. Any questions at all, folks, to start us out today? Okay, before we jump into 4.4, just to take a look into where we're at in the schedule, we scroll a little bit further on. We have an ordinary week coming up on week number 12. Then already on week number 13, we're coming into our third exam. That means on Friday of our current week number 11, I'm going to restart the same exact process that you've seen for both exams 1 and 2. I'll start by saying the exact coverage for exam 3, include the formula sheet, and then the sample exam exercises. So essentially, we're just going to do it all over again in the same kind of order for the upcoming third exam. So on Monday of this week, first thing in the morning, I'll be emailing everyone the course with the link to schedule your exam. If you're in the in-person section, it'll just be in the classroom as normal. So that's where we're at so far. June asks, will we have properties of logarithms, formulas on exam? That's a great question. I hadn't quite determined that for what to put on the exam exactly, but I think it's a good idea to include that. So let me make a quick reminder here. It'll say include properties of logarithms, or logs for short, for the exam 3 formula sheet. I think that'd be really helpful. That way we're focusing more on the calculus, and algebra is going to come secondary with that guide there. Naomi says, well, you'll be able to go over a quick review of what we learned before the break. I don't typically have reviews in our schedule because this course is so fast paced, but we're coming up to our last exam. So I'm going to open it up on Thursday. If you folks do have questions about exam 3, I won't hold a formal review, but I'll take exam 3 questions to start out the day. Other questions so far? Okay, once again, for the third exam, you'll know exactly what the coverage is, which sections. It's going to pick up right where exam 2 left off. So that'll be section 3.6 on exponential growth, exponential decay. But the same kind of problems we've done on WebAssign, on quizzes, the ones we've done on lecture notes, you'll see reconveyed on the sample exams I post down below here. So it's going to be followed pretty closely from what we've done in class, what you've done in the homework and quizzes, as well as the sample exams posted. Well, I think that's it for my announcement so far. Any last questions or comments? Okay, well, let's jump back in where we were. Section 4.4 on optimization. This is, again, probably not the best section to have split across from spring break, but that's just where the pacing of the course ended up for us this semester. So let's kind of refresh on what we were doing in this section. So as a warm-up, we're looking into the first derivative test. In the first derivative test, this one's been reformatted to give us an absolute maximum or an absolute minimum. To find that max or min, there has to be exactly one critical number that we're looking for, and we have to have these inequalities hold. If there's an absolute maximum in the problem, that means once we find that one critical number, the derivative has to be positive for all x's smaller than the critical, meaning it's increasing until it hits a critical value. Then it has to be negative for all numbers bigger than the critical, meaning once we go across the critical number, it's decreasing, so going down. If there's exactly one critical number, And these inequalities hold for all x less than c. And then again, for all x greater than c, we don't just have a local maximum, we will have an absolute maximum. And change the inequalities around, literally just flip them on both sides here, and you would have an absolute minimum. But this is just saying you're decreasing first, then increasing after the critical number, and that's what's leading to the absolute minimum. So it's very similar to how we used the first derivative test in section 4.2. Only difference now in the optimization section 4.4 is now all of our problems have context, and this time it's exactly one critical number, not 2, 3, or 4. So that's the test that we're about to apply. We actually haven't gotten that far in these notes before we went to spring break. We only found the critical number, and then we called it a day. But any questions at all, folks, on the refresher about the test itself? Okay, and again, because it's been a while, let's refresh what we were even doing right before we went on a long extended break. We were looking into a function called P. It's the rate at which photosynthesis takes place for some particular species of phytoplankton. So this is saying the rate in change in carbon per cubic meter per hour, so rate of photosynthesis, and it depends on a different input. The independent variable is I. I is going to be the light intensity in this lab where we're growing this phytoplankton. It's measured in 1,000-foot candles, and we read into the context to assume 0 means total darkness, since we're thinking about light intensity. And so the domain is I greater than or equal to 0, or as an interval notation, from 0 to infinity. The question was asking us directly, not the maximum value for P, but it wants to know what to set the lights to. For what light intensity will we get a maximum? So once we get to that light intensity, our work is done. And if you found what the value for P is, you're going beyond the problem. You wouldn't lose credit, but you didn't have to go that far. So we're using the first derivative test specifically on this one. The test calls for first find the critical number, and that's where most of the work really got involved in. Any questions so far with either the test or the review on the context? Okay, further review on this is, recall when it says critical number, what we mean specifically is we want to solve the derivative of P with respect to I, the PDI or P prime if you prefer, set to 0. So that's what's meant by the critical number. So the very first step in getting that critical number was we went to the function P and we differentiated it. This one took a good amount of work because this one is implying the quotient rule. So this line sets up the quotient rule. The derivative of 100i gave us just 100. And the derivative of this quadratic gave us a 2i from this term, a 1 from that term, and 0 from that since it was constant. So that's the end of the calculus part of differentiating. Then algebra on all the other steps was just to simplify it to make it easier to solve that equation, the derivative set to 0. So we distributed 100 through, we distributed negative 100i through, canceled our terms, combined like terms down to that level, factor out 100, and then once we got here, we continued to factor as a difference of squares. 4 minus I squared became 2 plus I times 2 minus I. And then once we got to this line right here, we're ready to get the critical number. We set the numerator to 0. That's this line. Then once the numerator is set to 0, we observe there's two solutions, -2 or +2. But we eliminate the negative since in this context, light intensity has to be positive. 0 is total darkness. Phytoplankton is dying. At higher and higher light intensities, we're just cooking it. But 2 is the critical number. Here's where the problem becomes more interesting still. It's easy to celebrate early when we get the critical number and say, we found that light intensity. This should maximize P. But that's not the whole story whatsoever. Anything could happen at a critical number. At a light intensity of 2, it could be maybe an absolute minimum. Who knows? We'd have to look further into the geometry of this function to know if it's a maximum or a minimum. But it doesn't even have to be a max or a minimum. A critical number like 2 could lead to neither a max or a minimum. So just to go back to 4.1 to connect that thought, the reason why we have to now do a part B, go even further on this problem, is because once we have a random function put down on paper, like this one, that's a random function, x to the power 5/3. We've looked at this a couple times. We differentiate it on this line, set it to 0, and found 0 is the only critical number here. It's a unique critical number, yet there is no absolute maximum nor absolute minimum. So for a random function like this f of x, or the one we're working on, the first derivative test will prove if you have a max, minimum, and it even will tell you if it's increasing on both ends like this one, if it's neither. So that's what we have to do next. We're redoing the steps that we took in section 4.2, pretty much verbatim, now with the first derivative test, and this one and only critical number, I is 2. So this is where we would have continued on if we had more time, but we weren't trying to run to the very final minute right before spring break. Any questions before we actually now do the first derivative test? Okay, here's what this test is going to look like next. We've got the critical number, and let me scroll to maybe this part. Here's the derivative where the red dot is in its most convenient and simplified form, the factored form. We have the first derivative test right here, but let's leave it here for easy reference. First thing we want to do is recall that there's a domain for our function p. The domain starts at light intensity 0. So this is not a x-axis, this is the y-axis for light intensity. Minimum value is 0 on this, and we found 2 is our critical number for light intensity. Now, next thing we're going to do is we need to determine, is the derivative positive or negative on this domain, this region between 0 and 2? And we want to determine if the derivative is positive or negative on this region as well, from 2 off to infinity. So we do two test values for dp di. Now, one thing that's a little bit tricky about this is if you plug 0 inside this derivative, you'd get the right answer. But the moment we said that the domain starts right at 0, you could look into our definition for the derivative. It actually doesn't include an endpoint of the domain because it's based on a limit, which is a two-sided limit, not a one-sided limit. So we would actually want to pick something like a 1, not a 0. So that's one thing that's a small technicality here. If you did pick a 0, I wouldn't be super picky as I graded that one. The domain, if you didn't consider to exclude the negatives, it's going to give you the right sign on this derivative. You just don't want your domain to go around -2. That's a critical number we eliminated. So to be as careful as possible, our first test point is going to be at 1, because that's within the domain, not at the endpoint. So let's test at, excuse me, I said x equals 1, but recall the variable is I, not x. At light intensity I equals 1 with unit 1,000 foot candles, the rate of change of the rate of photosynthesis, that's this right here, dp di, becomes equal to, we're using this version here for the derivative, dp di, so we're just plugging now 1 inside this function. That's going to be a 100 plus 3, times 3 times 1. Plugging 1 here is just going to give us 6 squared. And this whole quantity comes out as positive, which means back over here, the derivative is positive. If the derivative is positive, it tells us the underlying function, p, is increasing. And that probably matches with what our intuition is. We're looking at phytoplankton that are growing. They rely on photosynthesis for food energy. So 0 at total darkness, they're all just dying. But once we're out here, we have the lights dimmed quite a bit. Now they're turning on higher and higher. That just means photosynthesis is increasing. The brighter the lights, the better the photosynthesis, right? Well, maybe to a point. Remember, if we put the lights on too high, we are going to kill them. They're essentially going to cook. So there's a sweet spot. We hope it's at the critical number, but to prove that happens right at 2, we have to show it's decreasing in this region. So we pick another test value. 3 would work really good in this region, be larger than 2. So at I equals 3, dP di becomes, go back here, plug in 3 this time. It's 100 times 5. 3 here gives us a -1. The denominator is guaranteed positive with that outer exponent of 2 being even. Let's just throw this in for the sake of completion. 9 plus 3 plus 4 squared. There's exactly one negative sign here, which means the derivative is negative. And then it tells us in this entire domain, larger than 2, the growth rate, rather the derivative is negative, which means P is decreasing in this region. So we've done an analysis with the inequalities. We found greater than 0 here, less than 0 here, but greater than 0 is this part for an arbitrary function f prime. Less than 0 is this part. The critical number is 2. So once we found that it's increasing in a range and then decreasing the other range, exactly one critical number, that means we found the value that leads to the absolute maximum. We don't know what the absolute maximum is still, but you know what? The question wasn't asking for that. They just wanted us to analyze and tell us what light intensity should this be set to maximize P, the rate at which photosynthesis is taking place. So the whole question ends right at this stage. At I equals 2, the rate of photosynthesis is maximized. So once we show this analysis here, we have to show a number line, or this could be done in tabular form if you prefer. Show the signs of the derivative, positive, negative, include the test value for just the steps showing the work in this process. Then we can make the conclusion, and this is all steps of the first derivative test. What's interesting about this test is the hard thing about it wasn't the inequality that we analyzed here. It was about doing that derivative. That one was kind of a monster, getting through it and then working out all the algebra. Well, again, this is kind of a tough problem to come back from on the break, so we kind of analyzed it slowly, refreshing what it was all about. Any last questions or thoughts, folks? Finding out the critical number 2 that leads to the maximum. Okay, well, so far in these notes, we've done both the first derivative test, this one just here, as well as the second derivative test. That can't be the end of the notes. We're going to practice a couple more problems doing both of the tests. So here's what the next set of questions are going to look like. This one looks like it's a type of optimization problem dealing with economics, or maybe something entrepreneurial in a certain sense. It says a rectangular storage unit container with an open top is to have a volume of 10 cubic meters. There's not a lot of context on why we're building this, but we now know that it's rectangular, it's a storage container to set to that volume. And it has to be built with a certain kind of specification. The length of the base has to be twice the width. Again, not a lot of context to say exactly why, but we're going to run with that and say that whatever we're building here must meet that requirement. And here's where it becomes kind of an economics type of problem. There's different costs for the materials. The base of this storage container is going to have a cost of $10 per square meter. The sides, there'll be 4 sides altogether, will be at $6 per square meter. So it looks like it has a fortified base and the sides don't have to be as fortified. We want to find the cost of materials for the cheapest such container, which makes sense. In economics, we're typically trying to minimize something. If we're building a product for a company, we want to optimize by doing it as cheaply as possible. That doesn't sound nice, but that's a reality of business models and economics. So we're going to cheap out as much as we can on this and not try to spend a dime extra if we can. It says, do not round intermediate computations, round the minimum cost to the nearest cent. This is more to help out with some problems in WebAssign. This is a pretty multi-step problem, and sometimes in WebAssign, even if you're on the right track with everything, if we round too much in the middle, we could lose the whole question. And if you feel like that's happening to you, don't hesitate to hit the Ask My Instructor button. If I can determine you're just off by a small amount of rounding, I'll tell you the real value and indicate, oh, it's just a rounding error. You were on the right track. So that's the whole statement of the problem. What's new in part B, however, is it asks us to use the first derivative test or the second derivative test. And this is how an exam question or a quiz question would be written. It's really up to us to decide which is the optimal test on the problem. So we'll make a big deal out of that when we get to the step of using either test on deciding which one is easier to match the function that we're working with. Well, any questions, folks, with the statement of the problem? Okay, one thing that's tricky about this function is, or this problem, is that the function is not provided. That makes it actually kind of tough. On the next example, there's the function, and we just launch right into finding its critical number. It's a lot easier to work through. But this one's kind of like example 1, where we have to build the function. First thing we should do then is draw something out. It's kind of hard to build a cost function like this unless we can pull together the geometry of the problem and analyze the figure we're really working with. So we have a rectangular storage container. The length is going to be twice the width. And so this is probably what I would draw to build this out. I'm not an artist, so I practiced this before class, and I've learned drawing 2 squares is a good way to start. So here's my 2 squares. Kind of skew them off like this, try to make them exactly the same size. And now it becomes a rectangular storage container. Recall it has an open top. So there's a base, but there's no top to this. 4 sides and a base. So extend a line going this way. And to make it look 3-dimensional, make it easier on the eyes to see, when I extend the line going from this corner to the next one, this is the part that you wouldn't actually be able to see. So this is dashed out, goes to here. And I kind of have a second thought on how I drew that. So let me draw it like this, step by step. Same square, but I want to be able to delete one side as I go. Then from here to here, I'll just extend it that way. Here to here, we're just going corner to corner. And then again, to make it believable, from here to here, that should be dashed. That's something you wouldn't see because this face, the right side of it, is blocking it. So let me go just some dashed lines and then a solid line segment. So that's the parts you would be able to see looking into the box. And the dashed line segments are the hidden sides. So there it is. We have a rectangular storage container. It's got a base. It's got 4 sides, no top whatsoever on this. That's why we can see on the inner walls here. It says the length is twice the width. So let's make this be the length going this way. That be the width going that way. It's probably not perfectly to scale, but it doesn't have to be perfect. It'd just look weird if we called this the length and that the width instead. It'll also have a height, so we can put an H here next and then go from there. Yeah, this is not my best art, but thanks, Haley. Appreciate it. I think some of these figures can get really good if you're good at shading. And that's the thing in art that just completely is a mystery to me. There's no way I can shade this well to make it believable. So if it had to be a vase, it's going to look really, really bad. Thankfully, it's got angles, so that helps out a lot for drawing something like this one. Well, now that we have that, here's the next feature about it. The volume is going to be 10 meters cubed. We know that volume is length times width times height. If this was an exam 3 question or a final exam question, any kind of formula like this, even if it's a volume formula, I would cite in problem so that we're not too worried about random geometric formulas, especially if it gets involved. There'll be less noise, so we focus more on the calculus. So volume is also 10 cubic meters. So the length times the width times the height would be equal to that. And then other feature of the problem is the length of the base is twice the width. So one thing we can do now to include some variables other than L, W, and H, we want really just one variable. We can say that this is X. If the width is X and the length is twice the width, then L over here would just be 2 times X. Sadly, though, there's no way to relate the height with X whatsoever. There's only one sentence that gives a relationship relating the width to the length. So height needs a new variable. We can call it just, say, Y altogether. So there's our rectangular storage container. Again, no idea what we're doing with this thing, but we have a constraint, 10 cubic meters. We have a formula, and so now we can say volume is the length, 2x, times the width, just x, times the height, just y. And then, once again, volume is 10 cubic meters. So on the left-hand side here, we can substitute in 10 meters cubed equals 2x squared times y. So far, I've used just this information right here. We have a relationship between x and y and the total volume, 10 cubic meters. But beyond that, we still don't have a function. And that function has to be a cost function. And so that's where these two pieces of information are going to be used next, the material cost for the specific sides. But hey, it gets us started, and this information is going to be used somewhere. Any questions at the moment in building this cost function? Okay, essentially what we're doing in this example 3 is, wrong section, very, very similar to what we did in example 1. Here, it was a simpler situation, right? This one was kind of a warm-up example, starting to think about optimization. We knew that the sum of the two positive numbers was 15, and so we built an equation that looks like this. That's our constraint equation, and that's essentially what's going on with this equation. It's different, though. It's a volume is 10 cubic meters, but it gives us an equation to work with. And what we eventually did was we took this equation and we solved it for y. But the thing that we were actually minimizing was the sum of cubes. And that's kind of what's going on here. The cost function, the thing that we're actually minimizing, is going to be the total material cost for building out this kind of container. So now we're building a C function, which is much like this step right here. It will involve multiple variables, but we can eliminate it down to just one singular variable, x, by using the constraint equation, x plus y is 15. For us, it's this equation in the example 3. So the logic of how example 3 goes is entirely analogous to example 1. There's just a lot more mental noise here because now we have volumes and material costs that change per side. But think of that as well as the big analogy. And now let's start working into material costs. Let's focus on the base. There's just one side when we're thinking about the base. So I'll put this as just temporary highlighting. The cost for the base. It's going to be, well, it's $10 per square meter. So we have to take $10 per square meter is going to cancel if we multiply that by the area, because the area is going to be in meter squares as well. And this will give us a unit in just dollars altogether. So we're going to take $10 times the area of this base. So that's going to be $10. The area of the base is just going to be x times 2x, just length times width. You know, that's not a bad thing to throw in the notes. Let's put that in there. Length times width, just to show how they're coming together. So that'll be $10 times the length, which is 2x, times the width, which is just x. So this becomes altogether, in unit of just dollars, 20x squared. So as far as the base goes, once we nail down what x is going to be, that will tell us how costly the base will be itself. But then there's 4 more sides to take into account. We need the side costs as well. So we move on to the next sides. And the thing is challenging here is the sides have different areas. There's the front and back faces, and then there's the left and the right faces. They could have the same areas if x is just right, but, excuse me, no, they can't, because the length is going to be twice the width. So just by the way this problem is formulated, they will have different areas. So let's go carefully. Cost for front and back sides. So by the front and back sides, I mean this front face here with the temporary highlighting and that back side there as well. So front and back sides will have a particular cost. And again, we're going cheaper on the sides. All of it's going to be $6, whether it's the front and back face or the left and right side. So we're on the $6 per square meter. So if we take $6, multiply by the area of both of these two sides, this will once again just be a number in pure dollars. Well, these sides are exactly the same. So if we find the area once, we can just double it. So here's the doubling factor. 2 times area, which will be $6. 2 times the area of these faces are going to be the width x times the height, which is this value y. So x times y. So there's the area. And actually, sorry, let me rewrite this as, just for the sake of making this parallel, we're taking the width times the height. Let's then substitute in. So the cost for our front and back sides are going to be $6 times 2 times width is x. You try again there, x for width. Height is y. And so we get 12 xy for the front and back sides. Naomi asks, will a problem like this one be on the exam? Yes, this could be a potential exam 3 question or a final exam question. Tougher on exam 3 because we only have 75 minutes. So if this one is an exam 3 question, exam 3 is going to be shorter on all the other parts so that we have enough time to go through this one. More feasible on the final exam without adjusting the total exam length, but it's a possible exam question on either exam. Other questions at the moment? Okay, we're nearly there with the total cost on this one. And again, if this wasn't a question on, say, exam 3, I would have to make the rest of the exam a lot smaller to fit this question in. And I probably would want to make some design changes on this one to make it a little bit faster. Maybe something along the lines of cost for all 4 sides, or all sides what's together are $10 instead of a different cost for the base or the front, back, left, right sides, to make it a quicker question on exam 3. But now we're moving on to the last 2 sides. There's 5 sides altogether because it's an open top. Now we want the left side and the right side. So here's the temporary highlighting for those 2 parts. There's the left side, the right side. So let's indicate that this is cost for left and right sides. So this cost for both the left and right sides is still at $6 per square meter. There's still two sides that we're going to take into account. So it still has this format. We take $6, two sides of exactly the same area, so 2 times area. But the area formula is different now, so we have to be really careful on this next portion. This is going to be $6 times 2 times. The area here is not width times height, it's now length times height to get the area of these sides. So L times W. So that means it's going to be altogether, let's substitute in the values, $6, 2 times. In place of L, we have 2x. Times in place of W, or hang on, that doesn't look quite right. Let me backtrack on that. Sorry for the distraction on this one. When I said L times W, that's the base again. I got distracted, I suppose. That should have been length times height. Let me fix that one there. Length times the actual height itself, h, would give us the value y. So multiplying that all together, that's 4 times 6, so 24 xy. And now we just about have it. The whole problem so far was just to get to this spot, find the cost function c. Once we find the cost function, getting the critical number is not as involved, but building out these functions, even in, say, this problem right here, if I want to make this kind of question even shorter, it might be more similar to, say, example 1 versus this one right here. But both example 1, example 3 are possible exam 3 or final exam questions. The tough work is just building out those functions. But once we have it, here's what's going to look like. The total cost is, you could call it a f of x if you like. I'll copy the format of the problem and call it c. It needs to be c of one variable x for our methods to apply. So I'll hope for the best and call it a c of x and hope we can get it to that stage. Cost at x is going to be cost for the base, which was 20x squared. I'll drop the dollar sign at this point and just write it in this way. Then add the cost for the front and back, plus 12xy. Add the cost for the left and right sides, 24xy. And we have like terms. These are terms in x and y, so we can say the cost is 20x squared plus 36xy. So we've got a cost function finally. From this point on, we can find the critical number, then use either the first derivative test or the second derivative test, and we're on our way with this one. This one wants us to find the actual cost itself. So the last question, once we had the value for the independent variable, I is 2, the whole question was over. This one, we have to take that value, plug it back inside the cost function to actually get the minimum cost on this one. Well, next step is the critical number. And that's not too bad as a step as far as the steps goes. To get the critical number, take this function here and differentiate it with respect to x. But now notice, once we go to try to differentiate that with respect to x, there is one major problem here. We can't do a derivative when y is another function which does depend on x itself without finding out what that function is. So we go back up here. Here's the constraint equation that involves y. If we solve for y, we can substitute it back here. So let's take another step before we finalize this function. If we have 10 2x squared times y, rather 10 equals 2x squared times y, We can solve that for y and say y equals 10 divided by 2x squared, which would be 5. I'll write this one as a negative exponent, x power negative 2. So that 5x power negative 2 will go right back inside here. And once we make that substitution, it's not a lie when we say cost really depends just on x. So cost in terms of x is now 20x squared plus 36 x times, here's our next substitution, 5 times x power negative 2. And then finally, we can simplify from here on out. So cost in terms of x is now 20x squared. Let's see, 30 times 5 is 150, plus 30 would give us plus 180. X times x power negative 2 will give us x power negative 1. Finally, the dust settles. We've got the cost function. And our next stage truly is we can find the critical number. Now we can really differentiate this using our ordinary methods. There's no hidden implicit function y of a variable x inside of here, no hidden chain rule whatsoever to potentially miss. But there's one extra thing that could help us in this problem. Once you're building a function, or even once the function's just been provided, and you go to analyze it, it's a good idea to think in terms of what is the domain in that function in the first place. Sometimes the context will absolutely imply a domain, and knowing the domain is, in some problems, very, very critical. For example, if we didn't know the domain was positive values, we might not have known to exclude negative 2. And now we have a local maximum and a local minimum, not some unique absolute maximum at I equals 2. So same kind of struggle on this one. Once we write down that cost function, we should think in terms of what is the domain in the first place? It involves a variable x. So what is x? It's the width of some storage container. That's an implied domain as well, right? If that's the width of something, then one thing that would be really, really weird is if the width were negative. If you tell a company to build a container with a negative width, they're probably going to be pissed off. They're going to be very, very confused, not knowing what to do. Width can't even be 0 as well. In our prior problem, 0 was an allowed value because a 0 light intensity did make sense. But here, if width is 0, the volume is 0, and 10 cubic meters is a lie. So we can say here, just from this diagram, x has to be positive because it's a width. And let's just say it again down below here. Now that we have a cost function, x has to be bigger than 0. That gives us an implied domain. It's now from 0 with a parenthesis, not a closed bracket, off to infinity. Well, infinity is not a symbol you can put in here. There's typically going to be an upper bound. X can't be, say, 10 to the power 50. But without any kind of practical advice on where to end this, it's just an okay domain to write, infinitely long in this case. Okay, now we're truly ready for the next step. We've got the function. We know its domain. Now we're ready to get a critical number. But any questions or comments at this stage so far? Okay, as far as the critical number goes, all we do is we go back here, differentiate, set it to 0. So this is the not as bad phase. Take c prime at x. Now we're differentiating in the ordinary way. This would be 40x on this term. This one's not so bad either. This would be negative 180 x to the power negative 2. So there's our derivative 1. Now we're getting the critical number the moment we set this equal to 0 and solve. And this one's not so bad to solve. One strategy you could take is you could clear the denominators. you could add this to both sides. Let's go in stages. Let's say take 40x equals 100, 80 x power negative 2. So now, usually we wouldn't take this step, except that's really a power of x in the denominator, allowing us to clear the denominators. So we don't need to go with the factoring approach at all in this one. We could say this is 40x equals 180 over x power positive 2. Clearing the denominators now just amounts to multiply both sides by x squared. So go times x squared here, times x squared here. We get the new equation that 40 x to the power 3 is equal to 180. Now, I think we need a calculator at this point. 180 divided by 40 is a nice even 4.5. So x cubed equals 4.5. Still not solved, but to solve this, you just take the cube root of both sides. You can either write it in radical notation. I'll write it in this way. X equals 4.5 to the power of 1/3, same as taking the cube root. I think this will be slightly more advantageous for us because we eventually have to take that x, put it back inside the cost function to find the minimum cost. But that's only if everything works out. If that's going to be the actual critical number that leads to an absolute minimum in this problem. But so far we can say x equals 4.5 to the power 1/3, or the cube root of 4.5. This is the critical number of C, that cost function. So again, it's a pretty big adventure on this one. Building the cost function is a problem unto itself. So this feels like one long problem stuck together. But once we get to the calculus, it kind of just flows. This is a different kind of equation than we've solved before. We didn't have to factor out anything. But once you unpack the exponents, clear denominators, it becomes pretty straightforward. Any questions at all, folks, getting that critical number? Okay, well, in this problem, we're trying to find the absolute minimum cost, and we have to decide which test is going to be advantageous to us. Should we use the first derivative test or the second derivative test? And in this one, it all depends on how hard is it to take a second derivative. That function is not so bad. Second derivative is really, really fast. So for this particular problem, second derivative test, this one is the faster test because C double prime is rapid to compute. On an exam or quiz question, it'll be up to you which test you want to use. We'll go with the second derivative test for the sake of practicing it again, and it's the optimal test in this situation. But if you did this whole problem with the first derivative test, it's different steps, more steps, but you're not going to lose credit. You'll still get the full credit on the problem. So now to practice the second derivative test, let's pull it up. We did it once on example 1, but that was before the break. So let's kind of refresh on this one and recall how this next test should go. Now, this second derivative test, it's modified just like the first derivative test. This one is going to give us absolute extreme values. First thing we need is this part highlighted in yellow. That's just the critical number. We solved that when we took the derivative, set it to 0. We found the critical number, 4.5 x to the power 1/3. So once we found that, the next thing we do is we go here. We have to take the second derivative. And if we're looking for an absolute minimum, like this problem is asking for, we need to show that the second derivative is positive and that this is going to hold for all x in the domain of f. So this would be for a local minimum, just positive at the critical number. but we want the second derivative at x to be positive outright. So this one goes a little bit strange. We first do the critical number. We did that part there. Next part, let's focus on this that gives us the actual absolute maximum. Sorry for the distraction looking at the local minimum. This one gives us the absolute minimum, not max. All we do next is take the second derivative and somehow justify it's greater than 0 for all x. So here's what this test is going to look like. Derivative 1 is here, so second derivative, c double prime, at x goes 40, and we're halfway done. That's how we know this is the right test to use. This will be plus 360, x to the power negative 3. So there's our next cost function. But to really use this test, it has this downside right here. We have to actually show that that second derivative is always positive no matter what. And if you think about that, that's kind of alarming in a certain sense, because if you have something that goes 40 plus 360 and a value of x to a power negative 3, whether this is positive or negative actually depends on x. If we throw a 10 inside here, it's positive. Throw a negative, let's say, that didn't quite work out. Looks like it's always positive. No, hang on, that can't be right. Throw in a negative 0.1 here. Yeah, throw in 1,000. You've got a negative value. And that's going to invalidate our test. The second derivative test will fail if it's possible that this could ever come out negative. It literally has to be greater than 0, really, for all x in the domain. But recall, that's the domain. The domain is just positive values. If you're only allowed to put positive values here, say 0.01, something like this, that's for a very small width here. Recall, we can't put 0, so this is a very small value. The smaller I make these values, well, the bigger that this is going to get altogether. If we put in something like, say, 10 or 1,000, the larger value we put in here, the closer and closer it just gets to 40. 40 is actually the minimum that this one could ever be. So we can actually assert that this is, in fact, greater than 0 for all x in 0 to infinity, the domain of c. The cost function had a particular domain. X had to be positive, or 0 to infinity. And if you're only plugging positive numbers here, there's no chance to get a negative whatsoever. So we've matched up the requirement of the second derivative test. Because it's positive for all x in that domain, we have a conclusion for an absolute minimum by this test. I think this test, again, it's really awesome when it works because it's just so fast. You don't have to put down a number line. You don't have to test values, which is a lot of extra work to get through. You just crank out the second derivative if it's a fast one to compute. But this is the downside. Showing that it's always either positive or negative is what makes it possibly a no-go in some problems. Well, now that we found that, we have to actually get the absolute minimum cost. So here's our final conclusion on this problem. By the second derivative test, the absolute minimum cost is, we take the cost at the critical number, 4.5 to the cube root, but for doing that cost, we have to go back to this original cost function all the way here at the very top. Let me circle it temporarily up here just to make it pop out. So we really had three functions we had to analyze. The original cost function, which we built from scratch. The first derivative just to get a critical number, and then we're totally done with that in the second derivative test. Then there's the second derivative, but we don't plug the critical number here because we're looking for the absolute minimum. We take the critical number, we plug it into that original cost function to get the minimum cost, and this turns into 20 times 4.5 to the power of 1/3 squared plus 180 of 4.5 power 1/3 raised to power -1. So that's it thrown into this function here. And we can simplify this a little bit better. We can say that this minimum is going to be 20. 4.5 exponent laws will say power 1/3 times power 2 is to the power 2/3 plus 180. 4.5, do the multiplication of these two exponents, so we get power -1/3. And finally, here is the absolute minimum cost. We're going to need a calculator for this step. 20, 4.5, power 2/3 altogether. So we're up to $54, but there's more. There's the next term, plus 180, 4.5 to the power -1/3. So this storage unit of 10 cubic meters capacity will cost $163.54. This question was written a while ago, so it hasn't accounted for inflation in any sense. So we'll just stick with that number, $163.54. So we finally got there. This one, again, is quite an adventure. Any problem where we have to actually build the function from scratch is always one that takes a lot of extra steps in the middle. So this one, we started with a geometric figure, analyzed costs of the sides. After we used the constraint equation, finally we built out the function, and then finally we used the second derivative test. But once again, just for the sake of reference, this question was really no different than example one. We had to have a constraint equation, we had to build a function, substitute in a value to get in terms of x. We got a critical number by setting it to 0. This one, we took the second derivative and it was positive, which also led to an absolute minimum as well in this case. Well, any questions at all, folks, getting through this one? Oh, Naomi asks for about this step right here, the 1/3 power 2, the 180 power 4.5 1/3. That step right there came from taking this critical number, which was right here. We had to take that critical number, which was the side length, and then plug it into this cost function right here. It plugged into both spots, the value for x here, value for x here. So when we plugged it in, here's that value for x plugged into that spot and that spot. So we kept the 20 and 20 in that exact format. This outer exponent of 2 became that outer exponent of 2 down below. Likewise, 180, 180 carried down, and that's the outer power -1 coming from this step up here. Yeah, that's the thing that's really tricky about this one. Thanks for asking about that. That's possibly my fault as well, because when I was reading this out, I accidentally focused on this part. Second derivative at the critical number. If it's positive, it gives a local minimum. So that's probably my fault with that confusion there. Sorry about that. What we had to do instead was show second derivative was just positive outright. And then getting the minimum cost was plugging it back into the original function. Other questions at the moment? Okay, well, we've done basically 1.5 problems and we're still one problem to go on these notes. These are pretty long problems. So once again, I'll be pretty mindful when we do the real exam 3, when I write out the reviews and the upcoming next quiz, that I come up with a problem for exam 3 that doesn't take so long. If it's going to be something like this, I'll find a way to shorten it up one way, somehow, some way. And if it does come out as a longer question, I'm going to make sure that there's time enough to do all the other problems as well, so that the exam doesn't feel like it went from a 75-minute exam to a 100-minute exam, something like that. Well, last question we have on these notes will be this example 4 here. This is one I was trying to get to right before the spring break because the context seemed to kind of fit. But we're doing it after spring break, that's just as well. This one is really a problem about a topic called pharmacokinetics, which is the study in pharmacy of how a drug affects the biology, the metabolism of a particular person. Everyone's biology and metabolism is different from person to person. And so pharmacokinetics tries to answer the question of how is a drug of any kind going to affect an individual or people on average? This one's going to be how a particular drug is affecting a population on average. It's going to be about the blood alcohol concentration, abbreviated as BAC. This is the grams of pure ethanol per 100 milliliters of blood that's in your bloodstream. It says it's sometimes written as a percentage. And just for more context on BAC, blood alcohol content, in the state of Idaho, if you're driving and they breathalyze you, your blood alcohol content cannot measure higher than a 0.08. So that's the legal limit. I think 1 beer is going to get me pretty close, and 2 beers is going to get me there very quickly. In Idaho, if a driver's BAC reaches 20%, personally, that sounds like a medical emergency. That sounds like alcohol poisoning. But this is real. If they breathalyze you or maybe do a blood test to determine your BAC, and it's at 0.20%, I said 20%, that is definitely lethal, at 0.20% or higher, in Idaho, it triggers enhanced penalties such as mandatory jail time and a 1-year license suspension, even for a first offense. So that's the drama and interesting context behind this one. And so now we're assuming someone takes a very large shot of really hard alcohol, some kind of liquor. The pharmacokinetics of that liquor as it enters the bloodstream, or the blood alcohol content, is modeled by this function. And this is a pretty accurate model. And there's a whole category of models that look just like this, whether the drug is aspirin, Tylenol, something like maybe Vicodin, who knows? There's a pharmacokinetics that goes along with it. And this particular kind of model is called a surge function. And notice it's an exponential function. Well, to a point. There's also a variable t here. So it's not the same as the functions we saw in section 3.6, but it has some interesting similar features. What a good search function is going to do is show a low value. The instant that you take this drink, it starts going up. It's going to peak somewhere. And then your liver, your metabolism is going to diminish the drug in your bloodstream. To expect to see a peak of the blood alcohol content, we want to know at what time does it peak. We also know, just to see what legal penalties we're going to be in if this ever happens to us, and our biology is very close to this model, which again is for an average population. What will be the peak blood alcohol content itself? So we want both the independent variable and the output variable at the same exact time for this one. But this problem is nicer than the last one, you might notice. This one just gives us the function straight out. We want to first find the critical number. And once we have that critical number, we'll decide on the test, either the first derivative or the second derivative test. Well, any questions at all, folks, about the context so far? Okay, Well, it's again, a pretty interesting topic on pharmacokinetics, a whole class of models. And this is again where optimization shines. All of our methods in calculus are extremely applicable to these kinds of topics, whether it's economics, biology, pharmacology. And to start off this one, it's a good review of the product rule and the chain rule altogether. This is not the easiest derivative. So because there's two functions, this one times this one, let me reset my color coding, there's going to be a product rule. Now organize it this way. That's the first factor, and that's the second factor. So on level one, product rule. And we have to start by using the product rule. But once we do the product rule, we'll have to differentiate this function that's in green. It's an exponential function, but the input variable is not just t. That means on the next level, there's going to be a chain rule when we go to differentiate that piece right there. So the challenging part about this problem is not building the function, it's actually differentiating it and then finding the critical number right after. So let's go carefully. Let's see if we can get the derivative written down and go from there. So the derivative of the blood alcohol content, B at time t, is going to be organized by first, differentiate the linear function, 0.011t, copy the exponential, e power negative 0.02t, go plus for the product rule, copy the linear function, 0.011t, and then multiply by the derivative here of the exponential, times e to the power negative 0.02t. So that's the product rule all laid out. That's the first thing we have to put down on paper. And this derivative here in blue, it's really fast. It's just 0.11. But the next challenge is we also have to do the chain rule on this one. So let's use the strategy of divide and conquer. That derivative is tricky in its own right. In fact, I recall when we were doing the chain rule section, there were questions about doing this problem specifically that we came back to. So let's practice this one carefully as a good review on how this method is going to go. So separating out this function, let's just give it a new name. Let's call it y equals e to the power negative 0.02t. This chain rule is very tough in a certain sense. It's not easy to analyze which function is inner, which function is outer. It turns out for this one, the base function we're thinking about is y equals e to the x. But we placed inside where x goes a whole new linear function, negative 0.02t. Actually, let me revise. Let's call that e to the power t for the analogy there, just to keep the input variable the same. So this entire function right here is derivative we do second, inner. And the base e exponential, e to a power, is function one. The outer function is y equals e to power t. So this is our preliminary analysis on the chain rule. In place of where t was, we threw something else inside of there, making it the inner function. And now with that analysis, here's how the chain rule is going to go on this one. Y prime is going to be, in the order of these derivatives, do the outer derivative first, which means you're differentiating e to the power of t. And it goes like this, except we don't throw in t, we throw in a placeholder. That's the same strategy we took each and every time we did the chain rule. Then we chain on a new derivative. That's going to be derivative 2, the second one we have to compute, the inner function. And this entire thing, negative 0.02t, will go in both of the placeholders at the same exact time. So negative 0.02t here and here. So we're nearly done with this chain rule, but any questions or comments at all, folks, getting to this step here? Okay, let's finalize it. Y prime is now this. We can draw parentheses on this if we'd like. E power negative 0.02t multiplied by this. This is just a degree 1 polynomial, so we keep its slope, negative 0.02. Parentheses there just to indicate we are multiplying that together, not actually subtracting. And that whole thing plugs in right here by the red dot. So now putting it all together, here's what the derivative is going to look like. The rate of change of the blood alcohol content in the bloodstream for this person who took some kind of heroic shot of random hard liquor is going to be 0.011 e to power negative 0.02t plus 0.11t multiplied by this derivative, which we resolved down here, e to power negative 0.02t times negative 0.02. So there it is all together. We've got the derivative down. Next thing we want to get is the critical number, but really before even getting the critical number, one thing we should really do is simplify this as much as feasibly possible. And in this context, that would mean factor it as much as you can. Any questions at all, folks? Just getting through the derivative side before factoring. Okay, well, here is next the factored form. It has a greatest common factor, and that's pretty much all we're doing to it. B prime at t. First, notice the 0.011 is in both terms together, so that's convenient to factor out, not completely required, but it'll make the next steps a lot easier on the equation solving. 0.011. Now, the one thing we definitely want to factor out is the exponential. It's in both of the terms, so factor out e to power negative 0.02t. And here's what it leaves behind. It's a complete cancellation here, so it leaves just a 1. And the only stuff surviving here is going to be t times negative 0.02. Let me highlight these temporarily. So everything else was factored out. That leaves negative 0.02 t altogether. And now we've got it. That's its derivative in the most simplified form for our purposes, getting the critical number on the very next step. And you know, we're pretty close to getting that critical number. The trick to this is we'll set both factors equal to 0 and solve. But the basic e exponential never hits 0, so we only just solve this one. We'll solve that linear equation set to 0, and we'll find the time at which blood alcohol will peak. But we'll only know for sure that's the correct time once we run it through the next test, first derivative or second derivative test. Definitely, it's going to be rushing to try to get to those next steps. So when we come back on Thursday, here's where we're going to pick up. We have the derivative, we'll next get the critical number, and then choose a method to verify that we actually found the absolute maximum in this context. But any last questions or comments, folks, getting to this stage? Okay, well, have a great evening, folks. Again, welcome back from the break. Sorry it was short. They're always short, it feels like. Once we get through this, we'll be essentially done with the applications of the derivative. And the next section will start on Thursday. This is really just bridging the gap into integral calculus before we start chapter 5. So antiderivatives will be kind of a fun, interesting new topic, starting fresh with a different side of calculus. But have a great night, folks. I'll see you all Thursday. Thanks. Have a good one. You too. Have a good one. See you later.